in lecture 4, we were talking about several aspects of digital circuits. So we learned how to build digital logic functions using MOS transistors, MOSFETs. And then we started talking about some aspects of design. So one of the key aspects of design we learned about was noise margin and how to compute that for a CMOS NOT gate. Then at the end of the class, we were talking about limited fan in and fan out, which is the limitation on the number of inputs or outputs you connect to any logic gate. And we'll take a look at why this exists by looking at a circuit diagram. We also talked about propagation delay. If your circuit simply has one gate, because this circuit has only one OR gate, over here our propagation delay is going to be the same as gate delay. So propagation delay is for an entire circuit. A gate delay is for just one gate. The time it takes for the output of the gate to change after the input has changed. So the same kind of definition that is provided on the slide here. However, it is propagation delay is with respect to a circuit, gate delay is with respect to a gate. In this case, there is only one gate in the circuit, so propagation delay is the same as gate delay here. Now we'll look at where this fan-in limitation comes from. And in order to do that, we'll observe a two-input AND gate. So here we are observing a two-input AND gate, and we are considering that both the inputs of the NAND gate are high. So if I just draw the symbol of the NAND gate, say we have A, B, and some C. So A, B are the inputs to the two-input NAND gate, and C is the output of the two-input NAND gate. We know that we can build NAND gates using MOS transistors. So if you look back in your notes, you will see that we have built a NAND gate using two NMOS transistors in series that was in the pull-down network, and we had two PMOS transistors in parallel as the pull-up network. And if I treat the transistors as simple resistors, which can have a resistance very low or very high, indicating closed switch for low resistance and an open switch for a high resistance, then I'm just modeling those resistors as simply the resistor symbol. Now what is going to happen when, so that's my NAND gate, two input NAND gate, two NMOS transistors in series in the pull down network, and then two PMOS transistors in parallel in the pull up network. Then if you increase that number of inputs, so we are increasing the fan in over here. If you increase the number of inputs to 5 input NAND gate, we are going to add 5 NMOS transistors in series in the pull down network and 5 PMOS transistors in parallel in the pull up network. However, this could lead to a problem. If you have two low resistors over here, think about a voltage division rule. 5 volts is being divided in a parallel combination of two high resistors and a series combination of two low resistors. And for this particular case, if the resistors are low in value, even if you add up two low resistors, the resistance might still be low enough so that you get a low V out. The question on the chat box is, why is the transistor represented as resistor? So we are not representing the transistor entirely using a resistor. We are just representing it in the two extreme cases. So if you have an open circuit, we have used the transistor to indicate an open switch. And we did that by saying, for example, for NMOS, if the base voltage with respect to the source is very low, then the transistor doesn't turn on, meaning it is off, meaning the two terminals, collector and the emitter, I should say drain and the source, are not connected, meaning open circuit, which I can indicate as a resistor of very high value. And similarly, if it is a short circuit, when the transistor is on, I can indicate that as a resistor of very low value. So I'm only using that for the extreme cases, not for the entire operation of a transistor. And I'm only doing that to explain the repercussions of fan-in. So we all know that from Ohm's law, V is proportional to R. In fact, V is IR. So if R increases, voltage across that increases, which means if I have two inputs that are both high, I would want, right? So if this is high, for a NAND gate, I would want my output to be 0, low. However, if I have 5 of them connected in series, what would happen? My overall resistance over here would increase, right? It would be 5 times a low resistor, R. And if I consider a very high resistance, my output voltage increases linearly because of that. So my V out is probably going to be too high, and I may not get a low output in that case. So I hope you now see that there has to be a limitation of the number of inputs I can have to a gate, to a NAND gate. And for with the same reasoning, you can apply that for any kind of gate. It will break in some input condition. When the inputs are low, you will be fine for the case of NAND, because the high resistance, all these will be high R values. You are going to be okay, but it will break in the case of the inputs being high, which means we will have to include that in the design process. So that sets up the limitation on fan-in, or the number of inputs I can have to a logic gate. 2 inputs was okay. 5 input, very good chances it will break. So I'll have to reduce that to maybe 4. Maybe I'll have to come down to 3. 4 is a very common number. 4 input NAND gate. You see that in the ICs many times. If you can have a fan-in limit, similarly, you can also have the fan-out limit, or the number of things you can connect to the output of a NAND gate, or for that matter, any gate. So in this case, what you're saying is, there is a NAND gate, and I may connect that to several things. And there has to be a limitation on the number of things I connect at the output of the NAND gate. And this also happens because of the same circuit analysis reasoning. If you have a 2-input NAND gate with both inputs being low, if both inputs are low, then they are represented as 2 NMOS transistors that are represented using a high resistance, high R value. And if we do not connect any load over here, we have not connected anything to the output here, you can see that the output over here is just V out. We have not connected it. As opposed to here, we have connected 5 parallel loads. In this diagram, we have represented 3 parallel loads. that are connected to the output of the NAND gate. So coming back over here, no load Vout is high enough because it is measuring the voltage across two high resistors. So if it is measuring the voltage across two very high resistors, Vout is going to be high enough, which is what we want, right? Because we have 0, 0, you want your output to be 1 for a NAND gate. However, if you have a fan out of 5, meaning you have connected 5 things to the output of the NAND gate, all those are represented as 5 resistors over here. When you have, say, R1, 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 5 R1s. Let me just move this one level down. 1, 2, 3, 4, 5. Actually, there are 6 in this diagram. Anyway, it doesn't really matter. Just assume that there are 5 outputs that are connected. If you have 5 outputs that are connected and they all have the same resistors R1, what is going to be the equivalent resistance of all those in parallel? Well, if you have all those in parallel, it will be R1 divided by 5. So the value has gone down by a factor of 5. Because the R has gone down by a factor of 5, V also goes down by a factor of 5. Now, which means that V out is probably going to be too low. And we don't want that. We still wanted the output to be high, but we may not get it because we have connected too many things at the output of that gate that are effectively going to be in parallel. So I hope this is a quick discussion on why that particular limitation exists of fan in and fan out, explained using some basic circuit analysis techniques, essentially just resistors that can be connected in series and parallel, and the voltage division rule, which arises from Ohm's law. V equals IR, R increases, voltage across that R increases. All right, so questions about this? I'm going to stop the recording here, and for Boolean algebra, which is our next lecture, I'll start a new recording.